guys. So last time we started talking about the growth of functions, and I introduced what's called big O notation. Today I'd like to do a bunch of examples of big O notation and some other notations that I'll get into soon. You need to do a lot of these to get the hang of them. It's one thing to be able to recite the definition. It's another thing to be able to approach these problems. All right? So typically the way these work is there's a trick to doing big O, and there's a trick to doing big omega. And I'm going to show you these tricks, and you need to practice them so that when you see them on an assignment or a test or an exam, you know what to do. So to refresh your memory, we say that f of x is big O of g of x. That's the same thing as saying that there exist constants c and k that are both bigger than 0. And it's important that they're constants such that 0 is less than or equal to f of n is less than or equal to c times g of n for all n bigger than or equal to k. Whoops. For all n bigger than or equal to k. Okay, that's the, oh, I guess I should be consistent with my variables here. Let's say x for everything. Right, it doesn't matter what parameter you pass to the function as long as it's consistent. All right, so that's the definition of big O. That's not new. That's what we said last time. And the example we saw last time was the following. We wanted to show that 5x squared plus 10x plus 3 is big O of x squared. And we sort of know that this is going to be true because the thing on the right is x squared as the highest order term, and the thing on the left is a constant times x squared as its highest order term. So these highest order terms match, which means that the thing on the left should be big O of the thing on the right. Right? That's sort of our general rule. But that's not a proof. Right? That doesn't prove that 5x squared plus 10x plus 3 is big O of x squared. Because in order for me to prove that to you, I would need to show you c and k. Right? That's how you do a big O proof. You show me c and k, and show me that they're correct. So I have to do that. And the way I do it is, well, this thing here, the definition of big O, that's an inequality. So I want to prove that an inequality is true. So I start on the left, and I work my way to the right. Notice that I don't really need to do anything with this 0 because it's clear that this thing is going to be positive. Or at least it's going to be positive for all x bigger than k, for sure. All right, so I start on the left. So 5x squared plus 10x plus 3. And I want to prove that that's less than or equal to something. So I put down a less than or equal to symbol, and now I need to write down something that's definitely bigger. And I can't just write down anything that's definitely bigger, because I'm trying to prove that fx is less than or equal to c times g of x. Well, this thing here is fx, and this thing here is gx. So I'm trying to move towards a constant times g of x, so a constant times x squared. Now I can't just say this thing here is less than or equal to 5x squared and say, oh, c is my constant, because that's not true, right? 5x squared plus 10x plus 3 is bigger than 5x squared. So this isn't true. I need to do a little bit more work. And the work I'll do is I'll say, okay, well, I can definitely, if I have 10x over here, I can put 10x squared over here. And the reason for that is that 10x is less than or equal to 10x squared as long as x is at least 1. Right? Because if x is smaller than 1, well, when I multiply something by something smaller than 1, I get a smaller number. Right? If you multiply something by half, you get a number that's smaller than the original number. All right, so that's one step. The other step is I can say plus 3x squared because I have a plus 3 over here. And that's okay because 3 is less than or equal to 3x squared as long as x squared is at least 1. Because if x squared were, say, a half, then 3x squared would be smaller than 3. So is it clear how I've done this step? This is probably the hardest part, and the reason it's hard is because we're used to writing things that are very precise, right? We're used to working with equalities. That's what we're taught all through our entire math careers in elementary school and high school. What you probably don't get taught as much, and certainly not enough, is working with inequalities, and that's what we have to do here. Question?
Could you have just said, like, 100x squared? I mean, why 10? Where did you get those numbers?
Right, so you could say 100x squared. That would also be true. The reason I'm keeping it 10 is because I have 10 over here, and it's easiest to reason about this way. I know for sure that 10x is less than or equal to 10x squared as long as x is bigger than 1. It's also true that it's less than or equal to 100x squared. That's fine, but you're sort of changing more than you need to. It's not wrong, but it's easier to make a mistake that way. So in general for these, anytime I give you a function and it is in fact big O of another function, there are infinitely many c's and k's that show that it would work. Right? Any c that's bigger would do the job, and any k that's bigger would also do the job. Yeah?
And how do you know that x is always bigger than 1?
In general, you don't, but remember, I just need to show that this is true for x bigger than or equal to some k. So I look at all of the restrictions I have, and I'll do that in a second, and that will show me the value of k that I need to use. Yeah?
If you had technically correct values, but they were irrelevant, so like let's say you said k is 4, and
Yeah.
it's still technically correct, is that fine for the answer?
Assuming you had done the rest of the derivation, yes. What you can't just say is, oh, c's a million, k's a million, I'm done. Right? You need to do the derivation, but once you've done that, yes, you can say that. As long as it's clear that that's what you get from the derivation. Question?
Why was it less than equal to 5x squared, like that number right there, 5x squared?
So I don't change 5x squared because I know that I'm shooting towards proving it's something times x squared. So I want to keep that x squared there, and 5x squared is less than or equal to 5x squared, so there's no need to change it. I mean, you could say it's less than or equal to 6x squared. That's not wrong, but that's changing more than you have to. And I would argue that that's more likely to introduce confusion. But it's certainly correct. It's not wrong. Any other questions? All right, so the next step of this is to say, okay, well, I'm shooting for a constant times x squared, and now I have a bunch of terms that are all x squared, so I can collect like terms, and I get 18x squared here. And that's exactly what I'm going for, right? This is 18 times g of x, and this thing over here was fx. So this shows that f of x is less than or equal to 18 times g of x. So this 18 here is my c, and I know that looking at my definition. And what's my k? Well, I did a bunch of steps in my derivation, right? In all these inequalities I wrote down, I did a bunch of steps. And those steps were only true for certain values of x, right? So this step right here, converting the 10x to a 10x squared, that's only true as long as x is at least 1. And similarly, converting this 3 to a 3x squared, that's only true as long as x squared is at least 1. So I look at all of these restrictions I have on when my inequalities are correct, and then I pick the thing that's most restrictive. So the biggest of the restrictions, because in this case it's all x has to be at least this, at least this, at least this. So I pick the biggest one, and that's my value of k. Because I know all of my inequalities are valid as long as x is the biggest restriction in this case. Does that make sense? So, I mean, if I had x is at least 1 here, Well, if x is at least 1, then x squared is also at least 1. So as long as x is at least 1, this works and that works. And those were the only two restrictions I had, right? Those were the only two restrictions on the inequalities. So as long as x is at least 1, everything I did was valid. So that means my k is 1. So at this point, you see, okay, well, k could also be 2. That would also work. K could also be 3. That would also work. Anything bigger than 1, k could be. That's totally fine. That's not wrong. You could put your answer like that. I like to leave my answer as this because if I were in your position, being marked by the TA, it's very clear that 1 is the correct answer. You just look at all the inequalities you did, and 1 is valid for all of them. So yes, it's true, you could put k as 1,000, but if I were marking your paper, I would stop and take a second look at that and say, oh, that's kind of weird. And if you made a mistake somewhere, that probably would become more difficult for me to find you part marks. All right, so this is the example I did last time. I've done it again because it's really important that you understand what's going on. And this is the common trick for doing these big O proofs. Okay, you figure out what the highest order term is. In this case, it's x squared. You multiply through everything, so it's that power, and then you collect like terms. And after doing that, you get your constant c. And then you look at all of the steps you did in the inequalities. For things like this, it's almost always going to end up as 1, but we'll see examples later where k is not 1. And that gives you your value of k. Does this make sense? Yeah?
How would you disprove 1?
We'll see an example of that soon. Basically, you try to do this derivation, and at some point, you can basically do a proof by contradiction. Assume that it is big O, and you'll get a special kind of contradiction that we'll talk about. Other questions? Yeah?
Is there a sentence note hierarchy of like which terms are bigger than which?
I'll go over that at the end. Right now we're just looking at polynomials, and for polynomials it's the obvious thing, right? It's the power. I'll give a list of the other sort of non-polynomial things towards the end of the lecture. Other questions? All right, so let's do another example. And this example is very, very similar, but it has one sort of special difference. And that is that 5x squared minus 10x plus 3 is big O of x squared. So what's the key difference between this example and the previous one? Yeah, there's a minus here. Does that matter? I mean, yes and no. It's part of the function, so it matters, but can you easily get rid of it? Yeah, I want to write down something that's bigger, so if I ignore it, I'll get something that's bigger. If you don't subtract something, you get a bigger number, as long as that something is positive. So that's one thing you do have to watch out for. So let's see how this works. 5x squared minus 10x plus 3. I need to write down something that's definitely bigger or equal. And I can do that by writing down 5x squared plus 3. The catch is exactly that, as long as 10x is positive, or non-negative, we'll say. So this is true as long as 10x is bigger than or equal to 0. Right? That has to be the case, because otherwise it wouldn't really be minus 10x, it would be plus something, because the negatives would cancel. All right, so that's something you have to keep in mind. And now we have another polynomial, 5x squared plus 3, and you do the exact same thing you did before. Yeah?
Oh, no, I realized that.
Okay. All right, so now we know how to handle this one. This is, less than or equal to 5x squared plus 3x squared, which is 8x squared. So now I take c to be 8, using the same logic as before. Yeah?
Could I ask in the previous example and in this example, how can you assume that x is always going to be greater than or equal to 1 and that it would be less than?
Yeah, so if you go back to the definition, I just need to prove that there exists constants for which that's true. So I'm just saying there exists such a k such that once you're at that point, the rest follows. So it's not going to be true of all x. It just needs to be true of some. Yes, and as it happens, everything after that will also work. Yeah?
By saying that, are you making an assumption that x is greater than or equal to 1, or are you stating a condition for what that's true?
I'm stating a condition for when this big O definition is true. Typically, in the applications of computer science, x will be at least 0, and in fact it'll almost always be an integer, just because we usually use these to describe running times of algorithms, and in that case your input size is typically a positive integer, right? You don't sort a list of negative 10 things. But the definitions work completely even if that's not the case. And this comes up in math all the time, completely aside from computer science applications. All right, so for this example now, what is our value of k? Well, I forgot to put the restriction on the second one. This is as long as x squared is at least 1. All right, so we look at which of these is most restrictive. 10x is at least 0. What's that the same as? X is at least 0. And x squared is at least 1. What's that the same as? Right, it's x is at least 1. So if you say that x is at least 1, then that is satisfied and that is satisfied. Because if x is at least 1, then it's certainly also at least 0. So that's why you look at the most restrictive thing. In this case, this thing here is the most restrictive thing. All right, so that means we can take k to be equal to 1, just like before, and we're done. So this is the second trick for big O. And it's really just the same trick after you ignore the subtracted terms. So you can ignore a subtracted term as long as it's positive, right? Because if it's negative, you don't get a bigger number, you get a smaller number. Any questions? All right, so let's see what happens when things go wrong. So I want to know, is x cubed big O of x squared? So is it true that x cubed is big O of x squared? If we just sort of reasoned about this for a second, we would say, oh, well, the leading term of x squared is x squared. So it's to the power 2. The thing on the right, the other thing, x cubed, that's to the power 3. So we're saying, is something to the power 3 always at most a constant times something to the power 2? So is that correct? No, that's probably not going to be correct. X cubed grows faster than x squared. But this is saying that x squared, x squared grows faster than x cubed. So that doesn't match our intuition. But just because we're surprised by something or suspicious of something doesn't mean it's necessarily not true. So the way you usually attack these is by contradiction. So you assume that x cubed is in fact big O of x squared. So if that's true, what does the definition say? Well, then x cubed is less than or equal to c times x squared for all x at least k. And this is where c is a constant. That's what that's saying, if I sub that in. So now I have this inequality, and I'm going to divide through by x squared. So that's x cubed divided by x squared is less than or equal to cx squared divided by x squared. Right? I can divide both sides of an inequality by something. Now that's technically only true if x squared is bigger than 0. But is x squared always bigger than 0? Right, so it's definitely always going to be bigger than or equal to 0, because 0 squared is 0. But I know a little bit more information, and that's if I go up to my definition, I know that k is bigger than 0. So that means x squared which is the minimum value based on k, I know that that's always going to be strictly bigger than 0. Right? Because remember, if you multiply both sides by a negative number in an inequality, the inequality flips direction. But that's not happening here, so that's okay. All right, so that means, if I simplify this a little bit, x cubed divided by x squared is just x, and cx squared divided by x squared is c. So that's what that says. And my claim to you, and maybe you don't believe me, is that this is a contradiction. So why is this a contradiction? Yep.
Because if C does equal X, then X squared times C will be larger. It would be, sorry, equal to.
Okay, I think you're on the right track, yeah.
No function can be less than or equal, well, x, which grows in a straight line forever,
Yes.
can never be less than or equal to any constant as it grows on forever.
Right, so let's look at what's happening graphically. I have this function x, and it grows like this. It's a line. This is x. C is just a constant, so it always takes on the same value. It looks like this. And the statement is saying that x is less than or equal to c, but I can see that this is not the case, right? It's true up until here, but after that it's not true. Does that make sense?
I assume c can't be infinity.
Right, c has to be a finite constant. And that's really the critical thing. C is a constant, so eventually this line, which increases forever, will get bigger than it. So it's a little bit like this. You pick a number, so that number will be c, and I have to pick a number that's bigger than the number you pick. So if we play that game, I'll always win. Right? I can always pick a number bigger than the number you pick. That's essentially what's happening here. C is some fixed constant, that's the number you pick, and I can pick any number along that line x. And there's always going to be at least one number bigger than your constant. In fact, there's infinitely many bigger than your constant. So that shows that this is a contradiction. This is a contradiction because it says that x is always less than a constant. So if you have a function that's increasing, it grows and grows and grows over time, it never dips back down, that will always exceed some fixed constant. Yeah?
So let's say you keep trying to prove the inequality and you end up with restrictions that cannot be satisfied at the same time. Let's say you have a restriction that x has to be greater than 1 and x has to be less than 1. Is that enough to prove that it's not big O as well?
So at that point, it depends on what inequalities you've done. So if you're not careful with how you're stating your inequalities, it's possible to paint yourself into a corner like this. That doesn't necessarily mean it's not true, it just means you didn't make the right simplifications. So when you want to prove something is not big O, I prefer to go this route. Other questions? All right, so now we've seen both sides of big O. We have when you want to prove that it is big O, which you check by comparing the leading terms, the highest order terms, and you do that by putting every term to that power and figuring out your constant and restrictions that way. The other thing you do is to prove that it's not big O, and in that case you do a proof by contradiction, essentially, and you write down the definition and divide through by the highest order term, and you'll usually get a contradiction like this. This is the standard trick. So you need to be comfortable with both of these. All right, so now I want to tell you a little something about big O and how it's actually used. So typically, we want the function inside the O to be as small and simple as possible. So for example, 5x squared plus 10x plus 3 is in fact big O of, let me write something else, 2x squared minus 3x plus 4. That's true, but it misses the point of what's going on. Right? The whole point of big O notation is to simplify matters so that when we talk about the functions, we deal with very simple functions. If you write down something like this, it is technically correct, which is the best kind of correct, but not useful here. All right, so you can write this down, but if you were analyzing an algorithm and gave this as your answer, no one would be amused. The other thing that's true, I should say, but this is not useful. Well, I mean, maybe it's useful to you, but it's not useful to me. The other example would be, it's true that 5x squared plus 10x plus 3 is big O of x cubed. That is true. That's a perfectly correct statement, but typically you don't want to write that. So if I asked you for some kind of big O bound, I would be expecting the answer x squared. That's what's called a tight bound, and we'll talk about that more towards the end of the lecture. There's nothing wrong with this, but this isn't great. So if someone asked, how much does your house cost, and you said, less than $1 trillion, okay, but we were hoping for kind of a tighter estimate, even though it is correct. This second one gets used more, because as you start analyzing algorithms, sometimes the algorithm is too tricky to analyze. Right? So maybe I sat down and I worked really, really hard on bubble sort, and I couldn't analyze it for whatever reason, but I knew it was never more than x cubed. I couldn't quite get it down to x squared, but I couldn't prove it. I couldn't prove that it was x squared, but I know it's x cubed. Well, that kind of thing is kind of useful. Right? If you've worked on it for a really long time and you just can't quite finish it, it's better than nothing. But usually we like to get it to what's called a tight bound. All right, so this is true, but not very useful. And in fact, I should say it's not very informative. That being said, if on a test or an assignment I ask you to prove that 5x squared plus 10x plus 3 is big O of x cubed, you should do it happily. And it should be easy because it's definitely true. It's true with a lot of slack, if you like. Any questions about these guidelines? All right, so let's start proving some stuff about big O, about general functions instead of just these specific examples. So here's a very common one, and it's one that we basically already know, but we haven't proved it yet. So let's say that f of x is equal to a n x to the n plus a n minus 1 x to the n minus 1 plus a n minus 2 x to the n minus 2, and so on all the way down to a1x plus a0. So what is this? It's a polynomial. We have a few restrictions. We should have the restriction that a sub n is bigger than 0. Otherwise, this is kind of ugly, right? If a sub n were exactly 0, then it's not really a polynomial of degree n. It's really a polynomial of degree n minus 1. And if it's negative, the math gets kind of ugly. So I will say, sorry, I don't know why I put absolute value bars there. A n is bigger than 0. This essentially works. It basically follows through, but the math is ugly if you don't have this restriction. I mean, if you allowed it to be 0. All right, and I'll also assume that, that x is bigger than 1 because we're doing this analysis, but that will come up naturally anyway. So what I want to prove, that f of n is big O of what? What should this be? X to the n. And the thing that's implied here is that a0 all the way up to an are constants. So they're not variables of the function. The only parameter of the function is, sorry, this should be f of x. The only parameter of the function is x. All right, so let's do a proof. I want to prove something's big O, so I start on the left side and work my way to c times whatever's in the big O. So f of n is equal to a sub n x to the n plus a n minus 1 x to the n minus 1 plus a n minus 2 x to the n minus 2 plus all the way down to a1x plus plus a0. So now I need to write something bigger. The trick I usually would want to do is the following. I would like to combine all of these terms. Why can't I just combine all of these terms?
We don't know how many there are.
So I don't know how many there are, but I could write a summation notation, say. That's fine. Yeah? Right, so we multiply through, so they're all the same degree first. But why can I still not do that? What could go wrong? Yeah, the constants could be negative. I know the first one isn't, but maybe the rest are, there's a lot of them and they're all negative. And when I add them all together, I would get a c that was negative. And that'd be bad because if I go up to my definition of big O, I see that c has to be greater than 0. So that would be a problem. Yeah, absolute values is what we'll ultimately have to do. And you can see that this is a problem here, right? If I just said 5x squared minus 10x squared plus 3x squared and added them all together, what would I get? Minus 2x squared. And I can't set my constant to be minus 2 because the constant has to be at least 0. Or sorry, greater than 0. Yeah?
Did you already fix the constant value? You said a n is greater than 0.
I know that the first constant is bigger than 0, but all the other ones could be negative, right? And when I add them all together, I could get something smaller, small enough to make the whole thing negative. So I need to do a little bit more work. I know that this thing here, well, if I take the absolute value of all of these, then I only get something bigger, right? The absolute value of a negative number, if I take the absolute value, I get a number that's bigger, right? The absolute value of minus 5 is 5, and 5 is bigger than minus 5. So what I can do is I take a sub n and take the absolute value. In this particular case, that doesn't do anything because it's positive anyway, so that in fact doesn't matter. But it might matter here. All right, so now I'm ready to do my usual trick, now that I know that all of these are positive, and that's multiplying everything through by x to the n. And now I'm ready to collect like terms. This is just x to the n times an plus an minus 1 plus the absolute value of a minus 2 plus all the way down to the absolute value of a1 and the absolute value of a0. Okay? And now, well, I can just take this whole thing to be my c. the absolute value of a number is always at least 0, because the absolute value of 0 is 0. So I know this number is at least 0, but I need a little bit more. I need the number to be greater than 0, because C has to be greater than 0. Why do I know that this number is greater than 0? Yeah? Right, so I have one number that's greater than 0, and all of these numbers here are greater than or equal to 0. So if I add them all together, what do I get? Something that's bigger than 0, right? A sub n is at least a little bit more than 0, and everything else is at least 0. So the smallest this could be would be if all of these were 0, and then this one would be a little bit more. So overall, I get something that's bigger than 0. Right? Something bigger than 0 plus something at least 0 is bigger than 0. And that's why this assumption that a sub n is bigger than 0 is so critical. All right, so at this point, I can say C is equal to a sub n plus, or absolute value of a sub n, the absolute value of a sub n minus 1, the absolute value of a sub n minus 2, and so on. And what's my value of k? Well, k has to be bigger than 0. Yeah, 1 will do the job. And the reason 1 will do the job, well, is because, well, to go from here to here, x to the n had better be at least 1. And that's going to be true if x is at least 1, for sure. To go from here to here, that's only true if x to the n minus 1 is at least 1. And that's true if x is at least 1. And so on all the way up to here. This step here is true if x is at least 1, and that's true when x is at least 1. So all of those are valid as long as x is at least 1, so I can take k to be 1, and I'm done. So this is our first proof of something that's not just a straightforward function. This is a proof for basically all polynomials. Any questions about how I did this? Yeah?
Could you showcase when a n minus something is a negative number? Because I think if a n is whole positive, the first term, and the list or whatever, like the addition, like the sum stops when a1 x, in what case would that be negative?
So, I mean, that's this example right here, right? If I just had 5 minus 10 plus 3, I get negative 2. And that's not a valid C.
But then the first term has to be a positive thing, right?
Yes.
Okay, so then if you subtract 1
Subtract 1 from what?
from n, whatever n is.
What's n? There's no...
I'm talking about the example, like down here.
Mm-hmm.
This example.
Yeah.
Here you said that the first one is always positive, right?
Yep.
So
Mhm.
so you're constantly subtracting 1 and you're subtracting 2 from n. You stop adding them when a is 1 and x to the power of 1. So that means
So if I didn't add in a0?
no, the thing ends with a1 x to the power of 1, right? That's
Yeah.
when you stop summing them. And then there's
Well, no, I mean, there's still this a0. That's a0 x to the 0.
But for it to be for a n minus whatever and x to the n minus whatever to be negative, doesn't that have to have passed a0?
I'm not sure. Maybe we can talk after. I'm not sure I understand your example. All right. So, that being said, there are examples like this in your assignment. I would like it if you did not appeal to this proof, right? Because then you're missing out on all the fun. So even though we've proved this is true, this is the one exception to the rule that you can use results from class, you should sit down and derive C and K. Right? You need to prove that your values of C and K work. All right. Let's do another example. This is something we've already seen before. What is the sum of the first n integers? Or I guess I should say positive integers. So we already know what it is exactly. We know it's n times n plus 1 over 2. So if we wanted a big O estimate for this thing, what should that be? N squared, right? It is true that it's big O of n times n plus 1 over 2, but again, that's not the answer we're looking for because it's not very informative. We want something simple. N times n plus 1 over 2, that's a half n squared plus a half n, so it should be big O of n squared. So how do we see that? Well, 1 plus 2 plus 3 plus 4 plus 5 all the way up to n. That's definitely less than or equal to n plus n plus n plus n plus n all the way up to n. And how many n's did I write? I wrote n of them. So that's n times n, which is n squared. So what's my value of c here? One, right? There's nothing in front of the n squared. And what's my value of k? I mean, these are all true no matter what you do, as long as n is at least 1. So I can take k to be 1. Right? That's true when n is at least 1. All right. So this proves that the sum of the first n positive integers is big O of n squared, which agrees with what we did earlier when we were talking about summations, because we know that it's n times n plus 1 over 2. All right, let's see what else we can do with this. So far we've only seen polynomials. Let's see something that's not a polynomial. So what is the growth of n factorial? So for those who don't know, n factorial is 1 times 2 times 3 times 4 times all the way up to n. Right? You just multiply. So whereas the previous example is the sum of the first n numbers, n factorial is the product of the first n positive integers, I should say, sorry. So I want to know what the growth of this thing is. This is a little bit trickier. You could just say that n factorial is big O of n factorial, and of course you'd be correct. But that's maybe not illuminating here because we're asking about n factorial. This also comes up on the assignment, right? There's a question where you're asked to solve a summation and then compute a function that's big O of that. Well, if you just say it's big O of the function, that's not very informative, and you will lose marks if you do that, by the way. Yep.
Well, it's definitely big O of n times n times n times n times n times n to the n.
Yeah, we do the exact same trick we did in the last one, except instead of sum, it's product. So n factorial is 1 times 2 times 3 times 4 times all the way up to n minus 1 times n. That's definitely less than or equal to n times n times n times n all the way up to n minus 1, n times n, which is just n to the n. And here again I take c to be k to be 1. So n factorial is big O of n to the n. And as it turns out, that's a pretty rough estimate. That's maybe not a great answer, but we don't really know how to do much better than that anyway. What about the following? What is the growth of the log of n factorial? So the logarithm of n factorial. Any ideas there? Yeah? So why would you say n? Okay, so that's good. We have log n factorial, and we already know from the previous answer that that's less than or equal to log of n to the n. Right? That's what we had before. So what's log of n to the n equal to? Not quite n, there's an extra factor. n log n. Right? So remember, this is something that comes up a lot when you're working with logarithms. You need to be comfortable manipulating logarithms. And this is why they come up a lot in the analysis of algorithms. So when you have log of a to the b, that's exactly the same as b log a. And similarly, when you have log a times b, that's log a plus log b. And log a over b is log a minus log b. So if you're not familiar with those, if you don't remember them, you need to look them up. They're in the textbook. If you can't find them there, don't have the textbook, send me an email, come talk to me. I can go over them with you if you don't remember them. It's important to know them. All right, so therefore, log of n factorial is big O of n log n. And again here, c and k are both 1, right? Because there's nothing in front of my n log n, and this is all true regardless of the value of n. Because there were no restrictions on any of these, right? This is true for all n, and that's true for all n. At least n bigger than 1, because, well, certainly n bigger than 0, because otherwise the log isn't defined. So we just take 1. Usually when there's no clear restriction, you just take 1. All right, so moving on. How does log base 2 of n compare to n? So is log base 2 of n big O of n, or is n big O of log base 2 of n? How do these compare? Well, we know that n is less than 2 to the n. Do we know that? I never proved it for you. Does it seem like it's probably true? Yeah, I mean the exponential function grows way faster than the line. I will prove this for you later. We don't quite have the tools to do it now, or maybe we don't realize it. But that is true. So we know that n is bigger, n is less than 2 to the n, and I'll prove this later. Given that, you could take the logarithm of both sides of that inequality. That's a valid operation. I'll take the logarithm base 2. So log base 2 of n is less than log base 2 of 2 to the n. So given what I just said about the logarithm laws, I could write this as log 2n, and log base 2 of 2 to the n, that's the same as n times log base 2 of 2. Now what's log base 2 of 2? 1, right? Because 2 to the 1 equals 2. So this shows that log n is less than n times 1. So it's less than n. So again, log base 2 of n is big O of n with c equals k equals 1. Now this is another example that's not terribly informative, because there's a huge difference between log n and n, right? Just like there's a huge difference between n and 2 to the n. So you wouldn't say this, but it is correct. Right? This is correct. And you can tell that it's probably correct by a wide margin, because when c and k are both 1, that's usually a hint that this is somehow more obvious. Not always, but it's a good hint. Okay. So one thing you might have noticed is logarithms have bases, right? This particular logarithm had base 2. Up here I didn't actually specify what the base of a log was. And the nice thing is, as far as the analysis of algorithms is concerned, or the growth of functions, we don't actually care about the base of the logarithm as long as it's a constant. So typically the constant will be 2, e, or 10. It'll almost always be one of those. And those are all constants. And we don't care about it. So when using logarithms inside big O notation, the base doesn't matter. So why doesn't the base matter? Why doesn't that make a big difference? Anyone remember? Yeah.
I guess different bases don't actually do affect that.
Right. Different bases only differ by a constant. And if you don't believe me, well, just look at the change of base formula. If I have log base b of n, that's exactly the same as log base whatever, so let's say 10 of n, over log base 10 of b. So log base b of n is just 1 over log base 10 of b times log base 10 of n. So they only differ by a constant. So in fact, we don't even write the bases. As long as the base is the same, that's true. So they only differ by a factor of 1 over log b. And if b is a constant, then 1 over log b is also a constant. So that's why we don't usually write the base of the logarithm inside big O notation. It's the exact same reason you wouldn't write its big O of 2x squared. It's true, it's not wrong to write that, but typically you don't. And for the same reason, you don't include the base of the logarithm as long as it's constant. Now you could say something as log base n of something, and in that case it's not a constant, so you couldn't say that. But that tends not to come up, assuming n is the parameter of the function. Yep.
Does that apply to exponentials as well?
So 2 to the x being the same as 3 to the x? So that's a separate issue, and we're not quite ready to tackle that yet. But that is an excellent question. It's not immediately implied by this, though. Other questions? All right. So earlier in the lecture, someone asked for a sort of common hierarchy of these things, so I'll give that now. Here are some common functions listed from slowest So these are slowest to fastest growth, which means algorithms that have these runtimes are ordered from fastest to slowest. Right? Because the faster the function grows, the slower the algorithm will be. Because typically the function represents how long it takes. So big O of 1 is basically as small as it gets, in terms, at least as this is applied to runtimes of algorithms. This means the algorithm would always take constant time. So this is typically called constant time. And this would be something that doesn't depend on the size of the input. Right? So something like indexing into an array takes constant time as long as additions take constant time. So that still depends on your model of computation, but that's the classic example. The next biggest that's commonly seen is big O of log n. This is logarithmic growth. This would be something like binary search is the classic example of this. This comes up often in divide and conquer kinds of algorithms, which you'll see later on in your careers. The next common one you'll see is big O of n, and that's linear. Slightly bigger, so linear would be finding the max in an array, for example. The next kind you'll see often is n log n, and that's sorting using some algorithms. This one doesn't really have a name. The textbook tried to call it linear rhythmic, but that's not going to happen. Nobody's going to call it that. So typically you just say n log n. There's not really a short word for saying that. All right, the next common one is big O of n squared. This is usually called quadratic growth. And that's something like bubble sort, insertion sort in the worst case, and so on. A little bit bigger than that is big O of 2 to the n. In fact, a lot bigger than that. This is usually called exponential. And bigger still is n factorial, which we just call factorial. And there's others. So this is not an exhaustive list by any stretch. So there's infinitely many functions between each one of these, and infinitely many at the end. So there's many, many, many more functions than there are on this list. But these are the common ones that come up a lot when you're analyzing algorithms. So there's lots more than this, right? There's n cubed, n to the 4, n to the 5 between there. There's n log squared n log cubed n between here. There's n log n here. There's log squared n here, and there's log n here, just as an example. So there's tons and tons, infinitely many functions between any two of these. And in fact, there are infinitely many before here, before the big O of 1, but that doesn't usually come up when you're analyzing algorithms, at least not the runtimes. So here's a fun question. Are there countably infinitely many functions between elements of this list, or uncountably many functions between elements of this list? Yep.
Uncountably because there could be a number of rational and non-rational numbers.
Close. Do you have an example for why that's definitely going to be the case? Yeah. So for just the constants, that's not going to be enough because big O of 2, so 2, is still big O of 1. They differ by a factor of 2. Yeah, so one way to show this would be something about the real numbers. Where does that fit in here? So it's not so much that the output of the function is a real number. Yeah? So you're saying there's infinitely many outputs of these functions. I'm trying to say there's infinitely many functions. Yeah? What do you mean by that? Like n to a real number? Yeah, so I mean, that's the example I had in mind, right? You could have a polynomial that was n to the 1, n to the next real number, n to the next real number. But of course, there is not a next real number. So that shows you that there's uncountably infinitely many functions between each one of the things on the list. So all that to say, not everything is on this list, so please don't think that it is. All right, that's big O notation. Any questions? Yes?
I'm curious, where would O sine n fit in there? That would probably be between the first two?
So sine n varies between -1 and +1. The output is always between -1 and 1. So sine n is big O of 1. Other questions? So one thing you can think about for big O, and this is kind of a tough challenge question. I pose this when I teach third-year algorithms usually. Is it true that if you have two functions f and g, that either f is big O of g or g is big O of f? Is that something that's true? That's kind of harder to tackle, so I'll leave that for you guys to think about. It's kind of a cute problem. All right, so the next thing I want to talk about is big omega notation. And in some sense, this is the opposite of big O notation, big O provides an upper bound for a function. So big O provides an upper bound. And I know it's an upper bound because it's something like fx is less than or equal to c times g of x. Right? So I have an upper bound for f. It's c times g of x. Big omega provides the opposite. It provides a lower bound. So the definition is basically the same. So let f and g be functions from either the integers to the reals or the reals to the reals. For us, it's usually positive integers to positive integers, but it doesn't have to be. The definition applies equally well. So we say that f of x is omega of g of x. That's a capital omega. If there are constants, c and k, both bigger than 0, just like before, such that 0 is less than or equal to c times g of n is less than or equal to, sorry, I'll use the same notation as before. G of x is less than or equal to fx for all x at least k. So what's different about this definition? Well, the c times g of x and the fx switched places. Right? That's all that happened. So the definition up here was fx is less than c times g of x. Now it's c times g of x is less than or equal to fx. So you could write this as f of x is greater than or equal to c times g of x. And now you hopefully see that you have a lower bound. Right? C times g of x is a lower bound for fx because it's smaller or equal. So just like before, c and k are witnesses, and you can either write fx as an element of omega of g of x, or fx is equal to omega of g of x, although I just skirt the issue completely and say it's equal. Or say it is, sorry. So what it basically means is that after a certain value of x, f is always bigger than some constant multiple of g. G of x. And if you look back at the definition of big O, it's the opposite, right? Fx is always smaller than a constant multiple of gx. So that's all there is to it. Very similar tricks come into play, but they're slightly different, and I'll show them to you now. So is the definition clear to everyone? So let's do some examples. I want to show that that 5x cubed plus 3x squared plus 2 is omega of x cubed. Oops. And this seems like it would be true because the leading term of the left thing is x cubed, the leading term of the right thing is the only term, which is x cubed, and those match, so it seems like it would be a good lower bound, right? Question? Oh, how did that happen? Everything's fine. Undo? Control Z. All right. So, we want to show that 5x cubed plus 3x squared plus 2 is omega of x cubed. So let's do that. Again, we want to prove an inequality, and the way you prove an inequality is you start on one side and work to the other. So 5x cubed plus 3x squared plus 2. And now my inequality goes in the other direction. So I want to write down something that's smaller than the thing on the left. And my goal is to get to something, some constant, times x cubed. So how might I do that? What's something that I can write that's definitely smaller or equal? Yeah? Yeah, just 5x cubed. Right? If I ignore this 3x squared, I get something that's smaller. And if I ignore this 2, I get something that's smaller. This is only true as long as 3x squared plus 2 is greater than or equal to 0. Right? That's the only time I can truly ignore it, because if it's negative, then I can't leave it off. But we'll deal with that in a second. So this means I can take c to be 5. And when is it true that 3x squared plus 2 is at least 0? Always. That's always true for any real number x, because this is a parabola that opens upward, and its bottom point is 2 above the x-axis, so it will never dip below. So this is true for all x. So if it's true for all x, I would say take k to be 1. So I have c equals 5 and k equals 1. And I'm done. Yeah?
When you say lower bound, do you mean it's the best case?
No, not necessarily. So it can be sometimes used in a way similar to that, not in the sense of the algorithm, but in the sense of the complexity of the problem. It could also be used to bound the problem, saying this algorithm always takes at least n squared time. So bubble sort's a great example of that as we wrote it. So not the version that ends early, but the bubble sort we wrote takes omega of n squared time, because no matter what, it always takes n squared time. It always does exactly however many comparisons. This doesn't have anything to do with best case or worst case. It just has to do with the bound on the function. How we use it when analyzing algorithms, you'll see a little bit later. We don't usually use it so much in this course. This is just to set you up for later on. Yeah? No, so k has to be strictly bigger than 0. In this case, there's nothing wrong with that. In fact, it is true. But as per the definition, k has to be positive. All right. So let's see another example. This one's a little bit more complex. Show that x squared minus 3x plus 4 is omega of x squared. So again, we do a little sanity check and say, okay, well, the thing on the left is an x squared, the thing on the right is an x squared, so this seems like it should be true. So we try to prove the inequality. So x squared minus 3x plus 4. And now I want to write down something that's smaller. All right, so that's one way you could do it. What's the sort of thing that's making this tricky? Yeah? So you want to say this is bigger than x. Okay, but remember we want to shoot for something times x squared. So it becomes harder to introduce the x squared back. Yeah? X squared minus 3x squared. And leave off the 4, you mean? Right, so if you do this, that's equal to minus 2x squared, which would make our constant negative, which isn't allowed. So this relies on a trick we haven't seen yet. And I'll show it to you now. So what we did in the previous problem was whenever we had an added term, we just left it off. right? Because if you ignore an added term, as long as it's positive, you get something smaller. We could do that to the 4, but that wouldn't get rid of the minus 3x. We can't ignore that. So we do something else instead, and this seems really weird. But this is the trick. So x squared is exactly the same thing as 1/2 x squared plus 1/2 x squared. Everyone agrees with that? And we have this minus 3x plus 4. All right. Addition and subtraction are associative, which means I can bracket them however I want. So initially, they're bracketed like this. But what if instead I wanted to bracket it like this? I'm allowed to do that. I can bracket it however I like. All right. And notice what I've done is this was a minus before, and I've turned it into a plus. This is a giant plus. So this thing here is bigger than or equal to 1/2 x squared. But there's a catch. What's the catch? Yep. Right. This is only true as long as 1/2 x squared minus 3x plus 4 is greater than or equal to 0. So I need to figure out what the solution to that is. When is that true? So that's kind of tricky, right? You either need to solve the quadratic or do some trial and error. I'm going to tell you, for the interest of time, that that's true when x is at least 7, say. Not claiming that that's the best answer, but it's certainly true when x is at least 7. And if you don't believe me, well, that's 1/2 times 49 minus 21 plus 4. And is that going to make it true? Well, what's this going to be? 24.5 minus 21, 3.5 plus 4 is 7. And that's bigger than 0. And this is a parabola, so it's only going to get bigger after that point. So that does the job. So if I take k to be 7 and c to be 1/2, then I'm done. And notice that you don't need to figure out the smallest k, right? Because maybe 6 works. Let's see if 6 works. 1/2 times 36 minus 18 plus 4. Does that work? Yeah, 18 minus 18 is 0, plus 4 is 4. So that would also work too. But I happen to try 7 first, and 7 works, so I'm done. Now I'm only allowed to do this because I know that this is a parabola, right? It's a quadratic. So I know that it will just be increasing after that point. If I didn't know that, then I wouldn't be allowed to do this. There are other ways to solve these. Sometimes you can factor them nicely and then look at what the zeros are and figure it out that way. That's perfectly fine too. And the way you get these nicer answers is, well, there's nothing special about me splitting this up half and half. Right? I could have split that up however I like. So I could have done 1/4, 3/4. And some selections will allow you to factor this more easily than others. When I ask you something like this on a test, I will pick something where you'll be able to find it pretty quickly, assuming you factor it reasonably, or split it up reasonably. So think 2 or 3, or some other small or easy way to get the answer. On the assignments, because you have more time, it might be more work. Any questions about how I did that? So this is the usual trick for big omega with polynomials. You ignore all of the added terms, and then to get rid of the subtracted terms, you split up the leading term, the highest order term, and use that to simplify the rest. So typically, in a big O proof, the C is more work and the K isn't that much work. In an omega proof, usually the C is pretty easy and the K is more work. That's how it usually goes. There's always exceptions, but that's how it usually goes. Let's see what happens when things don't work out. So is it true that 3x plus 1 is omega of x squared? So we think to ourselves for a second and we say, well, the thing on the left is going to be of order x. The thing on the right is x squared. So this is asking, is x squared a lower bound on x? And the answer to that is no. It's not going to be. So the way we show that is exactly the same as we did for showing something's not big O. We do it by contradiction. So suppose that 3x plus 1 is omega of x squared. Then that means that 3x plus 1 is greater than or equal to cx squared for some constant c. And now what you do is you go ahead and divide through by x squared. So if you divide by x squared, what do you get? Well, what's 3x? Well, we can write it out in full. 3x over x squared plus 1 over x squared is greater than or equal to cx squared over x squared. So this is the same as 3 over x plus 1 over x squared is greater than or equal to c. So what, sorry?
Well, 3x over x squared, and that's 3x to the negative 1.
Yeah, and that's 3 over x. Yeah. So what happens to the left side as x gets bigger and bigger? It gets smaller and smaller, right? As x gets bigger and bigger, it does so in the denominator. So as x gets bigger, the right side gets smaller. So we have a situation that looks like this. And we have some constant c that's right here. And the claim is that the blue line is always above the red line. And we can see just looking at it that it's not. And the reason it's not is because on the left side we have a decreasing function. Right, so this is the game where you pick a number and I have to pick a number that's smaller, a real number. So this shows that 3x plus 1 is not omega of x squared. Does that make sense? All right, so for next time, I'm going to do a few more examples of big omega and then move on to big theta notation, and then we'll start the next topic in the course, which is another proof technique called induction. So that's it for tonight.
So there's also a k value involved in big omega, right?